All right, let's look at another rule here that's really helpful, and it's called the multiplication rule. To find the probability of two events occurring in sequence, you can use the multiplication rule. So a lot of times with probabilities, I think some of the easiest ways is to just think about what's happening. So think about your sample space and use your counts, your part to total. So if you can kind of just figure it out by counting, or you have a different method to use, that's okay too. But the multiplication rule can be nice if you're having multiple events in a row. It's just kind of a faster way to think about it than to try to do tree diagrams every time or something like that. So it says that the multiplication rule for the probability of A and B states the probability that two events A and B will occur in sequence is the probability of A and B is the probability of A times the probability of B given A. So this is your main formula here. Okay, so probability of A times the probability of B, given that A has already occurred, right? Because we're going in sequence. A occurs first, then B occurs. So you have those two probabilities. Now, a lot of times we're going to see that events A and B are independent of one another. So something like the coin and the die being rolled, where the probabilities are not getting affected. So it's easier in that case. You still have this multiplication, but for independence, remember that when things are independent, the probability of B given A is equal to just the probability of B, right? That a first event doesn't affect anything. So if you have independent events, we can simplify this and make it a little bit easier. Probability of A times probability of B. And then this rule can be extended to any number of independent events. So if I have 10 independent events in a row, then I can extend this multiplication rule. Again, it makes it much easier than trying to think about tree diagrams and all our possible outcomes. Very similar to the counting rule that we used before when things get a little bit more complicated. Okay. So again, these examples are different than the first one we started with, because in the first one, if you go back and read it, we were just looking at a single probability of finding, let's say, just a queen, given that the king was already pulled, or finding just a 6 on the die, given that we had a head. So we were really just looking at one probability. What's the chance of getting a queen? What's the chance of getting a 6? Now we're changing that a little bit. So you're going to see the wording change a little bit in the problems. It's very subtle, though. You have to really, really read these probability problems to see what they're asking for. That's probably the trickiest thing in this section, is watching for all these little tiny words that make a big difference. So here, 2 cards are selected without replacing the first card. Okay, so when you take your cards from the deck, you're going to pull one card, keep that one card, and then take your second card. So we're not putting that first card back in the deck once we've chosen it, right? We're holding it in our hands. We're going to use a standard deck of 52 playing cards. And we want to find the probability of selecting a king and then selecting a queen. So again, I just want to go back to that first example. A second. Okay. So look at this first example and the change in the wording. So in our first example, it said, find the probability that the second card is a queen, given the first card is a king. So we're finding the conditional probability here. Now look at my question. Find the probability of selecting a king and then selecting a queen. So we have 2 events here, not just the one event that's conditional. So we have 2 events here that we're looking at. So we want to know, okay, we're going to select that king first, and we're going to select that queen second. Okay. When you see this and idea, if you see and problems and probability, you want to think multiplication. So whether you remember that formal rule on the page before or not, if you see and, you're multiplying those events. You just want to be careful with your probabilities if you have independent events or dependent events. So the first case, what's the chance of getting a king? So think about your cards. You have 52 cards, nothing's been chosen yet, and you have 4 kings in the deck. So I have 4 kings that are possible to choose from, and I have 52 cards all together. Now you have that card in your hand. That king has been pulled. What's the chance of getting a queen now? Well, the queen, you have 4 queens in the deck, and you only have 1 card, you have one card less, so you only have 51 cards instead of 52 cards now, because you've already taken that king out. This is our probability. 4 out of 52 times 4 out of 51. Now, I didn't use the formula here on the page before. I'm recognizing that and means multiplication for probabilities. So I just took my time on the probability of each event happening, and then I multiply them together. Now, just to make this a little clear, we're using this rule here. Okay. This one is a conditional probability because these events are dependent. Right? So even though I kind of didn't make a big deal about it and write it formally, I recognize that pulling that king affects my total. So I do have a conditional probability here, but that multiplication process is still the same. So you find the probability of the first event, probability of the second event, just be really careful, think about it, and then multiply those together. So what we get here is 16 out of 2,652, or about 0.006. All right, let's do the second one. A coin is tossed and a die is rolled. Find the probability of tossing a heads and rolling a 6. Okay, so first thing that's going to happen is I'm going to toss a heads on my coin. There's my heads, okay? And then I'm going to roll my die and I want to get a 6. So those are the two things that are happening. I have this and idea here. So I need one and then the other. Well, the chance of getting heads on a coin, if you think of a coin, you have heads, you have tails. So there's two possible outcomes, and there's only one way to get heads, right? You either get heads or tails. So your chance of getting heads is 1 out of 2. For a die, you have 6 sides. You have numbers 1, 2, 3, 4, 5, 6 as options. So you have 6 total options, and only one of those sides has 6 dots on it. So I multiply these together. I get 1 over 12, which is about 0.083. Now, in this case, these are independent events. So the probability of getting a heads and a 6 is the same thing as the probability of a heads times the probability of a 6. I don't need a conditional probability here because I have independent events. Right. So again, for me, the way I think about probability is I really just always focus on part out of total for each event. What's the part? What's the total? How many ways can this happen, right? And I don't worry so much about the formulas. So if I see and, you're thinking multiplication. I can write my formulas out very formally. Your book loves to use the very formal notation here. But if you see and, you're just multiplying. So think about each individual event and what the probability is occurring there. And if you multiply those together, you should be okay. It should naturally either give you the independence or dependence if you think about what's happening in that scenario. So that's the way I like to do it. If you like to do a little bit more formal, that's fine too. So whatever works for you for probabilities. Again, big thing is just always keep in mind that part over total idea here. And watch your wording. All right, let's do another one. For an ACL reconstructive surgery, the probability that the surgery is successful is 0.95. Okay, so this is given in your text. We want to find the probability that 3 ACL surgeries are successful. So probability of 3 successful surgeries. Okay, so that's what we're looking for here. So think about this. This is actually an and statement, even though we're not using that word and, because what's happening? We want the probability of the first one is successful and the probability that the second one is successful and the probability that the third one is successful, right? So although I'm not using the word and here, if I think about this, I want the probability of 3 successful surgeries. That means the first and the second and the third all have to be successful. Now, these are independent events. There's no reason here why we would think these would not be independent events, that one person's surgery would affect another person's surgery, at least given the information provided here, right? So there's nothing that's underlying this information that we know of where one surgery should affect another person's surgery or their success rate. If my surgery goes well, it shouldn't affect if, John's surgery goes well, right? They're independent events. So the chance of each surgery being successful is 0.95. So the probability of the first being successful is 0.95. Probability of the second being successful is 0.95. And the probability of the third being successful is 0.95. And because we have an and idea here, we're multiplying these together. All right, so what we get is about 0.857. So the chance that all 3 surgeries are successful is about 0.857. So about 85.7% chance that all 3 would be successful. Find the probability that none are successful. Okay, so probability that all 3 are unsuccessful. So the probability that the first is unsuccessful and the probability that the second is unsuccessful and the probability that the third is unsuccessful. Now, again, I know I'm using kind of like loosey-goosey notation here, right? But for me, words just help. So if I can write it in words and kind of make it make more sense to me, that's what I like to do. So I'm breaking this down. I want the chance of probably that all 3 are unsuccessful. So that means the first and the second and the third have to all be unsuccessful. Now, they didn't give us the probability for something being unsuccessful, but we actually know it. The probability that something is successful, let's call that event A, is 0.95. Think about complements here. The probability that something is not successful or unsuccessful is the probability of the complement of A, right? It's the opposite. If it's either successful or it's not. There's nothing in between. So if there is a 95% chance it's successful, then there must be a 5% chance it's not successful. So we can use the complement here to get the other half. And remember that your event and your complement, when we take the probabilities, always add up to 1. So if you know one part, you can find the not version of it. So the probability of something being unsuccessful, even though it's not given, we do know it. It's 0.05. So these can be sort of like little puzzles. You want to really think about what do you know here? You must have enough information somewhere to figure this out, right? So think about what you know, use all those, tools in your toolbox and see if you can figure it out. So here, let me see, I have my work done out. It's about 0.0001. Okay, so a very, very, very small chance that absolutely none of them would go successful, which makes sense, right? If the chance of it being successful is 0.95, so 95% in percent form, then the fact that all 3 of them would fail would be very, very unusual, right? This is a very low probability. It's very unusual that that would happen. All right, another one here. Find the probability that at least one of the 3 ACL surgeries is successful. Now, this gets tricky. At least one. So I'm going to show you a shorthand way to do this too, but just think about this for a second. At least one successful. That means the probability that you have 1 successful or 2 successful or all 3 successful. So it gets quite complicated, right? It's at least 1. So you could have 1 being successful, 2 or 3. So these are 3 different probabilities we'd have to figure out. And it's different because for one being successful, it could be the first one, the second one, the third one. So you have all these different breakdowns you'd have to do in a tree diagram. It gets very confusing. So an easy way to deal with the idea of at least one is to use the complement. So think about the complement of at least one. Well, the opposite of at least one is none, right? If you have at least one successful, then 1, 2, or 3 could be successful. The opposite of that is that nothing is successful at all. So we can use the complement here as a fast way to figure this out. So what you're going to do, use a different color for a second. And I want you to highlight this formula because it gets used a lot. So the probability of something being at least 1 is the same thing as 1 minus the probability of none. And we use this idea a lot. Again, because that at least one idea gets very complicated, particularly if you have lots of different options, not just 3. It's very hard to do that tree diagram there and figure out those probabilities. It gets to be a lot of work. So we use the complement. And remember, the complements have to add up to 1. So that's why we're using that number 1 here. And we're subtracting the complement away. So the probability that none are successful in this case. Now, for this problem, we actually already know the probability of none being successful. We saw it right here. It's about 0.0001. So if I go ahead and subtract, I get about 0.9999 as my answer. So the probability that at least one of the 3 surgeries would be successful, it's not 1, it's not 100% guarantee, but it's very close. It's a 0.9999 chance that at least one of these is going to be successful. So again, I want you to just keep this little formula here in mind. Whenever you have this idea of at least 1, the easiest thing to do is to use the opposite or the complement. So it's often easy for us to find out the probability of none, and then we can subtract that with 1 to get the other side of it. All right, let's look at one more set of examples here. In a recent year, there were 18,187 U.S. allopathic medical school seniors who applied to residency programs and submitted their residency program choices. Of these seniors, 17,057 were matched with residency positions, with about 79.2% getting one of their top 3 choices. Medical students rank the residency programs in their order of preference, and program directors in the United States rank the students. The term match refers to the process whereby a student's preference list and a program director's preference list overlap, resulting in the placement of the student in a residency position. Okay, so a lot of times in the medical field, once you finish school, so to say, you're not quite done everything. You go into a residency program where you work at a hospital or an office, whatever you're doing, and you learn more there, right? So it's like continuing to practice. So a lot of times students will list their top 3 choices, hoping to get one of those 3 choices. So what it's saying here is about 79.2% actually got one of their top 3 choices, which means that about 20% did not get one of their top 3 choices, but they were placed. So let's see, for part A, we're gonna find the probability that a randomly selected senior was matched with a residency program and it was one of their top 3 choices. Okay, sorry about that. I just wanted to write some of our sets down. So let's let A be the set matched with the residency position and B be, not the set, but the event matched with one of the student's top 3 choices. So we have 2 ideas here. First of all, did the student actually get a residency position? Because not everybody did. And 2, did they get one of their top 3 choices? So notice also here we have a keyword and. So you have to really read carefully here. If you read it through too fast, you may miss that. So find the probability that a randomly selected senior was matched with a residency program. So we're looking for the probability of A, and it was one of the senior's top 3 choices. Now, we want to be careful here. So they were matched with one of his top 3 choices, given that they actually got a position, right? So you have students who weren't even matched at all. So we're talking that within this group, was it one of their top 3 choices? So you do have a conditional probability here. Again, very hard to see. So we have to really be careful here with these examples. So what's the probability that someone was actually matched? So it tells us that 18,187 students applied and 17,057 were actually matched. So your first probability is the 17,057 divided by this 18,187, right? Part to total still. And means multiplication. And then now we're looking at what's the probability that a student was matched with one of their top 3 choices, given they were matched for residency at all. And we do actually know that. So if we read here, it says, of these seniors, 17,057 were matched with residency positions, with about 79.2% getting their top 3 choices. So meaning that those who were matched, 79.2% got one of their top 3 choices. So this is your conditional. Given that you were matched, 79% got one of their top 3 choices. So I can take that 79.2% and put it into decimal form. So 0.792. When I go ahead and multiply those through, I can use my calculator here. I get 0.743. Now, when you enter into your calculator, I would do this first group first, leave that in my calculator, and then multiply by that 792. Find the probability that a randomly selected senior who was matched with a residency program did not get matched with one of their top 3 choices. All right, so notice here, this is a different question. I don't see the word and. I'm not saying they were matched and did not get one of their choices. I'm saying find the probability that a senior who was matched did not get one of their choices, right? So we are given that the student has already been matched, and we need to find the chance that they did not get a choice. So we're actually looking here for the probability of not getting their choice, given that they actually were matched. Okay, so again, these are really tough. You got to read really carefully here. Find the probability that a randomly selected senior who was matched with a residency position. So the senior was already matched. So we already have A occurring, right? It's the conditional probability. Did not get one of their choices. So the idea of not is the complement. So we're using B complement here to show that. Now, we can use complements like we did at the end of the last example. Remember that the regular event plus a complement event has to add to 1. It also works for conditionals. So for instance, the probability of B given A plus the probability of B complement given A would also be 1. So you still have that same idea. So I'm going to use the complement here. So 1 would be the total. And then if I subtract out the probability of B given A, I should get the complement, right? Because I can move this to the other side by subtraction. I know this value already. It's right here. It's that 0.792. And when I subtract, I get 0.2. And finally, would it be unusual for a randomly selected senior to be matched with a residency position and that it was one of the senior's top 3 choices? Okay, so we're talking about the senior was matched to the residency position and it was one of their top 3 choices. So we already found this probability. This is part A, right? We got the probability of 0.743. This is a large probability. It's pretty close to 1. So actually, this is not unlikely. It's actually not unusual or unlikely. It's actually very likely or usual, right? This probability is quite high. So it's quite likely that a student would get residency and get one of their top 3 choices, right? It's about 74%. So keep in mind that that 0.05 is usually your cutoff for unusual or unlikely events to occur. So if you're above that 0.05 threshold, then we consider that to be totally usual and totally likely to occur, or at least more likely to occur. And that 0.05 is our typical cutoff.